Okay, so we're talking about what it means to be a strong acid and a weak acid, and on the prior page we saw some examples of strong and weak. Strong means complete deprotonation, which means single arrow, which means no KEQ or KA or KC or whatever it is you want to call it. Weak means a double arrow, which means we'll have an equilibrium. The other thing about my list of 1, 2, 3, 4, 5, and now the next one is 6, is that you should commit these to memory, because while there is a system for naming acids, we are just going to leave it in terms of the few that we need to know. Okay, so HCl you should know is strong, and it's monoprotic, which means HCl, single arrow, H plus Cl minus. This is the acid, and if you go backwards, this is the conjugate base. Okay? Now, generally, but not always, you can recognize your acid because it has an H on the left-hand side, or maybe it has 2 H's on the left-hand side, or maybe even 3. Generally, that's how we teach recognizing acids in terms of Arrhenius acid, but moving forward, you can also recognize them as proton donors. Okay? Now, remember, if the acid is weak, you can write a KEQ, which we're going to call a Ka because the A means acid. So here are a couple of examples. HCN, double arrow, H plus, Cn minus. So our Ka expression is H plus, Cn minus, HCN. Okay, and then we can either find the values here. You've got some problems in your book that give you the values at equilibrium. You would plug them in, solve, and get a value in Ka, or you could look it up on a table somewhere. Okay, this one was on our list. This is acetic acid. Again, double arrow, pull a proton off. You have CH3CO2 minus. And our Ka expression would be H plus times CH3CO2 minus over HCH3CO2. You would get some information of your proton concentration at equilibrium, or your acetate concentration at equilibrium, or your acetic acid concentration at equilibrium, or you would go look it up on a Ka table. And because I'm a weird person, I happen to know that that's 1.8 times 10 to the minus 5th. Okay? H2S is diprotic, so we're going to pull one proton off, HS minus. We can write a Ka expression for that. Go look it up in a table. And then the second one, HS minus, double arrow, pull a proton off, S2 minus, Ka, we can write an expression for that. We can go look it up on a table. Okay? Now the upshot here is, how will you know if an acid is strong or weak? So 1, there's the list. Nitric acid, sulfuric acid, hydrochloric acid, those are strong. Carbonic acid, acetic acid, phosphoric acid, those are weak. Okay? Or you go look them up in a table somewhere. 2, it's going to have a double arrow. If it has a double arrow, that's inferring that it is weak. If it has a single arrow, that's inferring that it is strong. And 3, it's going to have a KEQ, which we're going to call a Ka, which you can figure out mathematically, or you can go and look up. Okay, now the reason that you care is that usually and typically you want to be able to calculate pH. Okay? Now pH is based on the propensity of water to auto-ionize. Okay? So I have water, double arrow, H3O plus OH minus. Now H3O plus really means H plus aqueous, right? we have an H plus, and we have some water, and that's how we get our H3O plus. Okay, now H3O plus is called hydronium ion, but it's really code for H plus, which means acid. Okay, so the double arrow means that it's going to have an equilibrium. And so what ends up happening is that we have 2 protons here, 2 protons here, kinetic in that water. Kinetic molecular theory says molecules move, 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 move. And sometimes they crash into each other so hard, oops, they don't pay me to do magic, right? That we go from 2 and 2 to 1 and 3. Okay? So 3 protons there, 1 proton there. And so this is called the autoionization of water, and it happens because molecules move. Now this is going to have a KEQ associated with it, but this KEQ is going to be called a KW. Okay? And the value of the KW is 1.0 times 10 to the minus 14th. And what this means is that the propensity of water to autoionize is very, very unlikely. Most water wants to stay as water, and this is good for us. Okay? This is good for us. On the other hand, a little bit of it will go forward. Okay? Which makes water, if it donates this proton, an extraordinarily weak acid. Very, very, very weak acid. Now there is some math associated with the autoionization of water and the value of 1 times 10 to the minus 14th. And these lead to the pH concept, and I used to spend some time deriving it, and I no longer do that. So suffice it to say is that the propensity of the autoionization of water leading to that KW gives us 4 equations that we can use for pH. One is that pH is equal to the negative log of H plus ion concentration. So you remember that the square brackets mean molarity or molar concentration. POH is equal to the negative log of the hydroxide. pH plus POH equals 14, and the fourth one, which is on the next page, is that hydroxide and H plus multiplied together has to equal 1.0 times 10 to the minus 14. And so what this means is that when these are equal, that's going to be neutral. We solve for this and we end up getting 1.0 times 10 to the minus 7 is equal to H plus. We plug that into this, we push log, we push negative, and we get pH equals 7 when these two are equal. On the other hand, if H plus goes down, OH minus has to go up. Or if H plus goes up, then OH minus has to go down because it's equal to a constant. Okay? Now the logarithm is a mathematical function based on powers of 10. And what you need to recognize about this is that each pH unit equals 1 power of 10. Okay? Each pH unit equals 1 power of 10. So when you're off by a pH unit, you're not off by a little bit, you're off by a mile.